נוריד את הרוח פה.
ואייל הוא התלמיד של הבינתחומי, של מה שמו, איך קראו לו? ראש הבינתחומי?
התוכנית הבינתחומית?
זה של ילד הבינתחומי, של אלקנה. הוא מהתלמידים של אלקנה. כן. והתלמידים האלה, יש להם, להרבה מהם, יש את החיבור הזה של להיות גם ריאליסטים וגם הומניסטים. כשאייל בא אליי, הוא התלבט אם ללכת לעסוק בהיסטוריה או ללכת למדעי הטבע. כי שני הדברים היו זמינים לו, והוא אחד האנשים המבריקים ביותר שאני מכיר. אני לא כותב מאמר בלי שאני מראה אותו לאייל, שהוא תמיד גורם לי לכתוב את המאמר מחדש, לעשות טלוויזיה של המאמר. ואני נורא מעריך אותו. והוא נמצא עכשיו בג'נליה, שזה אחד מהמוסדות המפוארים של אמריקה.
תודה שהזמנת אותי. אז אני אדבר קצת על העבודה.
למשל.
באנגלית? זה יכול להיות באנגלית.
באנגלית.
Okay. So, I'll present the work I did in Milan's lab, working together with Yoav also on the locomotion in mice, and Ilan asked me to present it because so the principles we use there were inspired by the movement notation. So we were thinking through that perspective when we were doing the analysis here, even though we don't use the notation itself. And so when I joined Ilan's lab, naturally everyone that was in the lab knows that you don't start with the question, you start with an observation. And for the observation, we build this arena where the mouse is walking on a glass and we can just look at the free behavior as the mouse is just exploring the environment. And it was important to have the environment large enough and to have the behavior as unfettered as we could have it. So, because the idea there being that then the behavior unfolds at its own pace. And we're not constraining it or forcing the animals to do things, and therefore we can find the logic more easily. And I'll just show you an example now of that will work. Of how it looked like, and this is just a movie of the mouse freely walking in the arena, and what you can already see is that the way that they walk, the gait that they use is a trot, or a trotting gait, which they move the diagonal legs together, alternating between the two diagonals. So after looking at these movies for a long time, we wanted to focus on turning behavior and what defines a turn and what makes a turn.
What do you call turning?
Oh, so that was the big problem of what is it. My naive approach to it before I started was that it's something like this, right? When the animal is walking straight, then it's walking straight, and when it's turning, then there's a discrete and very sharp event that happens. But naturally, this is not what happens, right? When the animal is walking straight, you can see that it can meander around a certain path, and even when it's walking or turning, it depends on what is the scale you're looking at, because part of that turn can be considered straight if you look at a different scale. So we decided to focus on the components themselves, the things that make up a turn, how the animal manufactures it, and understand the dynamics of it. And at a certain point, I was playing with the movies and just looking at the animals, and I connected these diagonals that I mentioned, and suddenly things started to make a lot more sense when I just looked at these two things and tried to understand turning from them. And some of it is already sort of apparent here, with the difference between when the animal is walking straight and turning. But I'll go into a bit more details and explain what was the insight we gained from looking at these two things. So here I'm just showing an individual step, and by connecting these lines we basically created virtual limbs. And as was mentioned before with the law of the heavy and light limbs, we looked at the heavy diagonal, which was the diagonal that is the base of support for the animal, the diagonal that the animal is actually standing on, and the light diagonal, which was the diagonal of the two legs that are swinging. And we also used the idea of changing the frame of reference, and our frame of reference each time was the heavy diagonal. And by that I mean that if we try to describe the movement of the animal when it's just walking, and we use the heavy diagonal as our frame of reference, then when the animal is walking straight, we can see that if we just measure the angle between these two diagonals, then the angle remains relatively constant when it's walking straight. The other very interesting thing was that another parameter that describes these two diagonals is the intersection point between them. And as I mentioned, we use the heavy diagonal as our frame of reference, and the front paw was our 0 point. And that was because for a step, if we look at the intersection point and what happens to the progression of that intersection point throughout the step, when the step ends, you see that the intersection point progresses towards the front paw. And when the step ends, it ends when this diagonal reaches the front paw, as you can see here very clearly. And this is not just for this particular step. You can see when we look at the sequence of step, and here I'm plotting 6 different steps, and like in the movie we saw earlier, where you saw sort of like the weight of the movement. Here, these are the light diagonals moving on top of this heavy diagonal, and you can see that the step ends when it reaches the 0 point of the front paw, and this one now becomes the heavy diagonal, and the blue diagonal is now light, moves across the red diagonal, and becomes heavy again, and this is how it alternates when the animal is walking straight. And this is sort of captured here in this representation, where now I'm showing the intersection point. Again, the 0 point is the front leg, and this is the angle between them. And you can see each line here is an individual step, and the angle is relatively constant. It's not changing much, and the steps all end when the mouse reaches the 0 point. So this is one of the building blocks the mouse uses to generate its motion. But when we looked at the movement further, and again, because we didn't constrain the motion of the animal, we saw also different types of building blocks. So in this one, when the mouse is turning and the front paw that is leading the turn is going in the same direction of the turn, then the angle between the diagonals is increasing, and the intersection point stops short before the front paw. When the front paw that's leading the turn is from the contralateral side, as the side that the animal is turning to, you get the opposite effect, where the angle is decreasing and the diagonal is crossing over the front paw. This is what you can see here clearly, that it goes over. And this is basically how these 3 different types of either the angle remains constant and the step ends at the 0 point, the angle is increasing, and the intersection point ends on the positive side, or the angle is decreasing and the intersection point is negative. And by concatenating these elements and alternating between them, the animal is able to generate turns. And here I'm showing almost a U-turn that the mouse did. And in this representation, you can see clearly you either have a step where angle is decreasing and you cross over, or angle is increasing and you're stopping short. So that was the idea, and these were like the inspiration behind these ideas, and the way we were, like Ilan mentioned in the beginning, that this was basically it's the language that helps us think about the problem and conceptualize it in these terms, and find the building blocks that the mouse was using to just walk freely. That's it. Thank you very much.
It's about 60 years that people studied locomotion. I mean, the study of locomotion is about 60 or 70 years old. But it was always performed by restricting the animal in a straight alley. So it's very typical that all behavioral science studies behavior. Since behavior is complex, so they simplify the behavior and they study the simplified behavior. And our principle has been to leave it in its full complexity and decipher it in its full complexity. And this is because we have the movement notation. The movement notation, that's what he used the word unfettered. So it unfetters, we unfettered the study of locomotion from the straight alley. So all of a sudden, all the richness of stepping behavior opens up. And the animal is not just walking straight, but it is also steering. And you have here both the mechanism of forward progression and steering together.